this episode, we're going to make name resolution feel predictable instead of mysterious by walking through what Linux is actually doing when you type a name and expect an address back. New learners often treat name resolution as a single thing called DNS, and they assume every lookup is a trip out to the internet. On Linux, the reality is a layered decision process that can consult local files, system services, and network-based resolvers, sometimes in an order you would not expect. When something fails, the error can look like the network is down even when the network is fine, because the system simply cannot translate a name into an address. The goal here is to build a mental picture of the moving parts, especially hosts, resolv.conf, and nsswitch.conf, so that when a question describes odd behavior, you can explain it without guessing. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is the difference between a name and an address, because the operating system must bridge that gap for almost everything network-related. A name is what humans use because it is stable and meaningful, like a server name in a lab or a website name on the public internet. An address is what the network uses to deliver packets, and that address might be IPv4 or IPv6 depending on the environment. When a program wants to connect, it typically asks the system for the addresses associated with a name, and the system returns 0, 1, or many answers. That means the program itself is usually not doing raw DNS. It is calling into the operating system's resolver mechanisms. The important beginner insight is that name resolution is not just one file or one server, but a chain of decisions that can succeed in different ways or fail in different places. The file called hosts is one of the simplest pieces, and it exists because sometimes you want a local, guaranteed mapping from name to address. Think of it as a tiny manual phone book that lives on the machine, where you can declare that a particular name means a particular address. Because it is local, it does not require a network, it does not time out, and it can override what DNS would say if the system is configured to consult it first. This is extremely useful for lab environments, for initial bootstrapping when DNS is not ready, and for certain forms of troubleshooting where you want to test connectivity to a known address while still using a name. The exam likes to test this concept because it reveals whether you understand that Linux can resolve names without ever asking a DNS server. A common failure mode is assuming DNS is broken when, in reality, the host file contains an outdated entry that is sending traffic to the wrong place. Once you understand hosts, you can appreciate why name resolution needs an order, and that order is controlled by a file called nsswitch.conf. The NAMESERVICESWITCH system is essentially a policy layer that tells the operating system which sources to consult for different kinds of information. Names are not the only thing this affects, because users and groups can also be sourced from different places, but for our purposes we care about host lookups. The key value of nsswitch.conf is that it defines whether the system checks local files first, then network, or the other way around. And it can also define whether a failure in one source should stop the search or allow the next source to be tried. This is why two Linux machines on the same network can behave differently when resolving the same name, because their policy order is different. For troubleshooting, you want to remember that nsswitch.conf is the traffic director, not the phone book itself. A common way to think about nsswitch.conf is to treat it like a decision tree that starts when a program asks, "What is the address for this name?" If nsswitch.conf tells the system to consult files first, then the host file is checked before any DNS activity occurs. If a match is found, the search ends right there, which means the network might never be touched. If the host file does not have an entry, the resolver then proceeds to the next source, such as DNS, where it may contact configured resolvers. If the policy is different, the system might try network resolution first and only fall back to hosts under certain conditions. This matters because it determines not only success, but the kind of delay you experience when something is wrong, like waiting for timeouts before a quick local fallback is considered. When you see a lookup that takes a long time, One possibility is that the system is waiting on a network resolver first, even though a local mapping would have been sufficient. Now we can talk about resolv.conf, because this file is where the system learns which DNS resolvers to ask and how to shape those requests. At a high level, resolv.conf specifies one or more resolver addresses and can include rules that influence how names are constructed during lookup, such as search domains that are appended when you use a short name. The key beginner point is that resolv.conf does not store the answers to name resolution. It stores the instructions for how to ask for answers. If the resolver addresses in resolv.conf are wrong, unreachable, or pointing to a server that is not responding, name resolution may fail even when the rest of the network is working. Another subtle point is that resolv.conf can be managed by other services that rewrite it, which means changes might not stick the way a beginner expects. From an exam perspective, it is enough to know that resolv.conf is the configuration for DNS querying behavior, and that incorrect entries create predictable failure patterns. Search domains are one of the most frequent sources of confusion for new learners, and they can create failures that feel inconsistent. A search domain is a suffix that the resolver may append when you look up a short name, such as looking up server 1 and having the system also try server 1 plus a local domain. This is useful in environments where you frequently reference local hosts without typing their full names. The downside is that a misconfigured search domain can cause the system to try names you did not intend or to resolve to an unexpected host if multiple possibilities exist. You might also see behavior where a short name resolves on one network but not another because the local search domain differs. When questions describe that fully qualified names work but short names do not, or that the wrong internal host is being contacted, the search domain behavior in resolv.conf is often the hidden cause. The mental model is that the system is not only translating names, it is sometimes generating candidate names before translation even begins. With hosts, nsswitch.conf, and resolv.conf in mind, you can now understand the most important set of failure modes: wrong answer, no answer, and slow answer. A wrong answer happens when a name resolves to an address that is valid but not the one you meant, which can be caused by outdated host entries, incorrect DNS records, or a search domain that points you to a different host with the same short name. A no-answer situation happens when the system cannot resolve the name at all, either because no source contains the mapping or because the configured resolvers cannot be reached. A slow answer situation is often a timeout story, where the system is trying a resolver that is unreachable or trying a sequence of sources in an order that delays success. These three patterns matter because the symptom you observe, such as connection refused versus name not known versus long delays, often maps directly to one of these categories. For an exam question, identifying which category fits best is usually the step that earns the point. Another failure mode that deserves attention is the difference between resolving a name locally and reaching the resolved address over the network, because beginners often merge those into one problem. Name resolution can succeed perfectly while the connection still fails due to routing, firewall policy, or service availability. Conversely, the network path can be healthy while name resolution fails, which makes it look like the network is broken when it is not. This is why earlier we used the troubleshooting chain that checks routing before DNS, because it forces you to separate reachability from translation. When you see error messages that explicitly mention the name, that is a clue that translation is failing, but when you see errors that mention a numeric address or a connection timeout, translation might have succeeded and the failure is elsewhere. The important habit is to ask yourself, did the system get an address? And if so, what happened next? That single question helps you place the problem in the right layer. Linux can also handle multiple address families, and that can introduce a subtle resolution failure pattern that feels like randomness if you do not know to look for it. A name can have both IPv4 and IPv6 records, and a system might prefer one family over the other based on policy. If IPv6 connectivity is broken but IPv6 answers are being preferred, the system may try the IPv6 address first, wait, and only later fall back to IPv4, which looks like a slow or unreliable network. In other cases, the program might take the first address returned and never try the others, so the preference order becomes critical. For beginners, the takeaway is not to memorize record types. but to remember that a single name can map to multiple addresses and the selection logic matters. When an exam scenario mentions that a system can reach some sites, but others are slow or inconsistent, dual stack resolution preference can be part of the explanation. Caching is another internal detail that influences how name resolution behaves, and it can make failures persist even after you think you've fixed the configuration. A cache is simply saved resolution information that avoids repeating the full lookup process every time. Caches can exist in different places, such as within applications, within system services, or within upstream resolvers, and each cache has its own lifetime rules. The most important conceptual point is that you can change a DNS record or correct a host's entry and still see old behavior until the relevant cache expires or is refreshed. This is one reason people feel like name resolution is haunted, because the machine appears to ignore the fix. On the exam, caching shows up as questions about why a change does not take effect immediately, and the right answer often involves understanding that name resolution is not a pure real-time query. Your mental model should include the possibility that the system is using a stored answer even if the configuration now points elsewhere. It is also helpful to think about how nsswitch.conf influences failure behavior beyond simply choosing an order. The policy can specify whether certain kinds of failure should end the search or allow the next source to be tried. For example, if a network resolver is unreachable, the system might treat that differently than a case where the resolver responds but says the name does not exist. Those are two different kinds of failure, and the resolver policy can decide whether to fall back to a different source in each case. This matters because it changes whether a missing DNS server completely breaks name resolution or whether the system can still resolve certain names through local files. It also changes how long lookups take, because waiting for unreachable resolvers causes delays that can affect application performance. When exam questions describe timeouts and long delays rather than immediate failures, it is often hinting at policy and network resolver issues rather than missing local entries. A particularly tricky beginner misconception is thinking that resolv.conf is always a reliable, manually edited file, when in many systems it is treated as generated configuration. Even if you do not dive into the specifics of which components manage it, the conceptual point is important. Some parts of Linux networking are controlled by higher-level services that may rewrite configuration based on network state. That means you can have a situation where name resolution works on one network, breaks on another, and then changes again after a reconnect, all without you touching anything. From a troubleshooting mindset, you respond by focusing on what the system is currently configured to do, not what you believe you previously set. Exam questions sometimes simulate this by describing that a configuration keeps reverting or that changes do not persist, and the correct reasoning is to suspect a managing component rather than assuming the file is static. The deeper lesson is that Linux configuration can be layered, and name resolution is a prime example. By bringing all of this together, you can build a clear internal narrative of what happens when a program looks up a name. The program asks the system resolver for addresses. The resolver consults nsswitch.conf to decide which sources to query. Local sources like hosts may be checked first depending on policy, and if network resolution is needed, the resolver uses resolv.conf to learn which DNS servers to ask and how to construct candidate names. Along the way, cached answers may shortcut the process. Address family preference may influence which address is tried first, and different failure types may trigger different fallback behavior. Once you can tell that story smoothly, troubleshooting becomes a matter of locating the first step that does not match expectations. That is exactly what the exam wants from you, because it is testing understanding of systems behavior, not just recognition of file names. At the end of this lesson, the main thing you should carry with you is that name resolution is a controlled process, not a mystery, and the controls are visible and reasoned about. The host file is the local manual mapping, resolv.conf is the instruction sheet for how to query DNS and how to expand short names, and nsswitch.conf is the policy that decides which sources are consulted and in what order. Failure modes become easier when you categorize them as wrong answer, no answer, or slow answer, and then you link those categories back to which part of the process could cause them. You also learn to separate translation problems from reachability problems so you do not chase the wrong layer. With that mental model, you can read a scenario and immediately ask, Is the system failing to translate, translating to the wrong place, or translating slowly due to timeouts or policy order? When you can answer that, you are no longer stuck, and you can move through Linux networking with confidence instead of frustration.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.